computation, communication, and control. So these are the three concepts behind this. Yes. So in the communication here is how we can able to communicate between M2M and IoT. So that is two concepts here. So machine to machine and IoT. So how the communication protocols are being helpful. Then computation. So algorithms. So computation is mainly on the algorithm. So how what kind of algorithms are set for cyber physical system. So in operating system, you might have studied about startup job first, then FCFS, first come first serve. So then function queue scheduling. So some of these algorithms we might have studied, but cyber physical systems it's slightly different. So EDF, that is earliest deadline first. So earliest deadline first algorithm. So then RMA algorithm, that is rate monotonic scheduling. Rate monotonic scheduling. So then IRIS, so increased reward, increased service algorithm. Increased reward, then increased service. So likewise, these are all some of the real-time scheduling algorithms that are not suitable for general operating system. So those algorithms are being helpful for the computation of cyber physical system. Then finally, we have the control system. So in the control system, we have multiple things called as feedback control system. So feedback control system, then digital control system. So that's what this control system is all about. Have you studied any topic on control systems? Any subject? Anyone?
Yes, sir. Yes, sir.
Yes, you have. Okay. So you might have studied control system on state transition. So using Laplace variables, how you can. Okay. Okay. So those things that is control. So in this case, computation and communication, that is part. It's coming computation on computer science, then communication on electronics, and control on public. So this is what all about the cyber physical systems. So you are learning almost all the three circuit branches that is part of this cyber physical systems. So that's how you have to be comfortable with all the three technologies. So computation, communication, and control. So generally talk about it. Generally what we do is through sensors and actuators in a feedback loop. So here I have a system. I have an input, then I got an output here. So before being when to give the output, so I have a feedback system. So this feedback system is sent back to the input for further optimization. So this is called the feedback control system. So the output we are receiving it here and the input it is there. So the input is mixed along with the feedback system. So together the system is improvising it. So that's how the way the output will be getting a refined output. So cyber physical system is all about this refined output with zero errors or sometimes very limited errors or we call zero errors. Okay. So some examples you can see robotic heart surgery. So the sensors that will be owned by the doctors and they will be performing it through the robots. So that's how the robotic surgery will. And target rescue inside an unknown floor plan inside a building. So inside a building, so if someone during the fire evacuation, if someone is stuck up inside, so you can send robots to evacuate them. So during those cases, how a robot handles the human beings, how it can go inside. So that's how the rescue system. And city traffic control system. So that is one city traffic control system. So how can you establish the traffic control system? So maybe what I do is by Monday I will show you a demo on Sumo. Urban mobility, simulation of urban mobility. I will show you a demonstration during our laboratory session. Maybe we will have one lab exercise also on this Sumo, so that you will understand how autonomous cars work and how this traffic management system works. So all these things are cyber physical systems. Okay, so any real life scenario that have real time guarantees, we call it as a cyber physical system. So they were been also called as embedded systems. They were been also called as networked embedded systems. But what makes the difference? We will see in shortly. Okay. So now some of the features here, the features here for CPS is reactive computation. So that is system that acts based upon the inputs and the outputs called reactive system. So that means the set of the associative inputs you are sending and you are getting some output. Between these two, so in what time duration the output you are receiving it. So that's we call it as reactive. So that is reactive systems. So how my algorithm performs in a system. So that is reactive. So one good example here is when initial days there was feature phones. Then touch phones have come. So the touch phone, they call two types of touching. One is resistive touch, another is capacitive touch. Now next they call it as capacity with refresh rate. Okay, so likewise the technology in display is also coming up. So in the resistive touch, what happens is you cannot have multi-touch. So the touch response will be very less. Maybe like if you see 20 millisecond or 10 millisecond. So once you touch it, it has a response of 20 milliseconds. Then capacitive touch. So they have 5 milliseconds, less than 5 milliseconds. Now less than 1 millisecond also there. So some phones have less than. And refresh rate. So 75 hertz refresh rate or 144 hertz refresh rate. Likewise. So these things are reactive computation devices. That means at what time when you touch your phone, maybe I'll switch on my camera so that I can show you my faces. So my face visible? No, right? So I could not switch on my camera as well. So anyway, I don't know what's the thing. Anyway, fine. So actually, I was in the campus, so but for the class, I just came fast to my home. Okay. Anyway, no issues. So that is reactive computation. So that means now the refresh rate in the phones have come up like this. So that means the touch response will be very good. That means the reactive computation. That means the time by which I apply the pressure on my touch panel, in what time the panel reacts. That is this kind of thing called reactive computation. That means I give the input and waiting for the output. In what time the output I will be getting. That is one. Next thing is concurrency and parallelism. So in concurrency, see generally in flowchart what happens is usually when we draw a flowchart, so start then checking some condition yes or no or something like this. So this is yes and this is no and this is some between a fuzzy condition. Then what happens? A small diagram will go here and small thing go and somewhere it will go and then it reaches. So flowcharts are not concurrent. That means if there is a condition no, then the cycle of operations will be different. The condition is yes, the cycle of operation is different. So there is no concurrency. That means parallelly everything will not run at the same time. So completely flowchart is not concurrent. But these kind of cyber physical systems are concurrent. Again, I'll give you a demo on this. Make space -J8. Okay, so this one command in Linux. Okay, so when I compile something, J8 means I'm going to compile with 4-core processor. So 4-core processor I'm going to compile. J16 means 8-core processor. So I will be compiling with the 8-core processor. So that means what happens is if it simply by giving make command, it will be running on any of the core. Even if you have 16 cores, even if you have 100 cores, but the algorithm will be running on only one core. The compilation happens only on one core. But when I use J8 means all the 4 cores, my compilation will be running. So that is what the concurrency is all about. So that means concurrently I can execute the task on all the all the processes available in my system. So that's we want parallelism or concurrency. Anyway, I'll show you some examples during our next lab class. I will show you the one example bubble sort algorithm. How can I find the execution time of a bubble sort algorithm? So how long it takes to get compiled? So bubble sort, you know, right? So comparing two elements, if one is bigger and another is smaller, keep it as it is. If the first one is bigger and next one is smaller, swap it. So then first iteration or second iteration, third iteration, fourth iteration, like that. The lowest possible, that is O of n square. So that means the computation time is so large, so that for 10 samples is fine, 100 samples is fine, 10,000 samples is fine. But if it is 10 million samples, if it is 1 crore samples, If it is 10 crore samples, then obviously the bubble sort algorithm will be the slowest one. Then how can I use all my core processor to make it run? So that is what the concurrency and parallelism comes into picture. So this is again one of the features of CPS. Next thing is, as we discussed, feedback control of the physical world. So that means how in the control system, when we give the feedback, what happens? So that is on the feedback control. So feedback control systems are proven that these are all the best systems available for any good performed system. So that is a feedback. Next thing is real-time computation. So here modeling time delays, system performance, and time-dependent coordination protocols and resource allocation strategies. So real-time computation means so how I can able to compute something with real-time guidelines. So real-time is generally real-time means it is task with deadline. Task with the deadline. Okay. Now what I tell is now the time is around 5:05 or 5:10. Now I'm just asking, for example, if I just tell you by 6 o'clock you have to submit an assignment. For example, today 6 o'clock. Now the time is around 5:06. So almost I'm giving a deadline of 54 minutes deadline for you. That means within 54 minutes you have to submit an assignment. So that means it is a real time computation. But by exactly 6, if you submit it, it's fine. Before 6 also, it's fine. But after 6, what happens? Let's say you are telling, sir, I will be submitting by 6:10, or I'll be submitting by 6:35. I'll be submitting by 7 o'clock. In the case, what happens? Your mark will be reduced. So, means your system is still running, but with a slight performance degradation. So, in real time, that's what we have three kinds of real time systems: soft, hard, and firm. So soft deadlines, that means the deadlines conditions are soft. The real-time guaranteedness is soft. Even after the deadline is not met, the system will not be in danger. It will be, the performance will be degraded, but still the system will be running fine. That is soft deadline. Hard deadline means once a task is not meeting its deadline, the system will be catastrophic. So the action will be catastrophic, will be in danger. The system will might get collapsed. There will be a collapse of the system. So one good example for a hard deadline, I'll just tell you, Kalpana Chawla, where she died. Most of you might be knowing about she was she went to space, and the particular space shuttle was about to land in the Earth station in the next 15 minutes. There was a deadline not met by a particular task. It's a small temperature controller. They didn't meet this deadline. Because of that, the entire space shuttle get crashed, and there were some cost of at the cost of some human lives. So that is what this hard deadline. So hard deadline systems will be a collapse if the deadline is not met. One good example is another is aircrafts. So inside the aircraft, they have some deadline. Some tasks will be having deadlines while they land and while there is a takeoff. So something wrong happens. So automatically there could be a collapse of the entire aircraft. So that is hard deadlines. In between, we have something called as firm deadlines. So firm deadlines, generally we call it as fault tolerant systems. Fault tolerant. So fault tolerant system means they can able to tolerate some amount of fault. So they can incur some fault tolerant system. One good example is during power shutdown. So let's say there is heavy rain outside. There were thunderstorms also. Suddenly there is a power cut. Okay, so suddenly there's a power. You feel that there's a sound, a blast sound. So something is get blast. You got a sound. That means your nearby transformer got a blast, and within the next 20 minutes to 30 minutes, you will get the power up. So the power is up. So that means there were some fault tolerant system because those generally transformers are fault tolerant usually. So, but they are not smart, but they are fault tolerant systems. So in that case, within the next 10 to 20 minutes, so you feel that the entire night there will be no power. So how do we sleep? So all these things you might, but in the next 20 minutes the power will come up. So because those systems are tolerant to some faults. Okay, so that is the firm deadlines. So real time generally of soft real times, hard real times, and firm real times, and even stock exchange also. So stock exchange servers, they are all of fault tolerant because some, let's say if Biden have announced some kind of strict policies in H1B visa, then immediately Indian stocks will go down. So how it will come up again? So many people will be now that time go for trading and then pulling their money. So in that case, how the system runs or how the system handle the fault. So that is from their deadline systems. So, and generally, finally, we have safety critical applications. So mostly CPS are useful for safety critical, mission critical, or we call safety and mission. So mission critical means mostly the critical applications always associated with deadlines. Okay. So in that case, these are the features of CPS. So some of the softwares that are used for CPS. So we'll be seeing these softwares. Upal, it is for modeling and verification of time-based systems. Then Ptolemy, modeling and simulation of hybrid systems. Hybrid system means all the physical system and non-physical system. So both of the systems we can use it. And automotive software for smart automotive sectors, we use these softwares. So this software only we'll have a demo by Monday. Maybe I'll show you the demo by Monday so that you will understand. Oh wow, such kind of softwares are there like that. Actually, this software is initially it was by some private people. They have released the source code freely. So, but later on, the German government have taken over the software. Now the German government is running with this software, simulation of urban mobility. That's what we call it as SUMO. So I'll show you that. Here I'll show you any of the map in our country, and then I'll show you how we can able to make the traffic management as well as the cars. I'll show you. Then MATLAB, as you might have done MATLAB for dynamical systems, and SpinRoot. I don't know about what is this SpinRoot. Anyway, there's a software, and VHDL. So you might have done some digital systems on using VHDL or Verilog. So these are the two softwares that they do for synchronous modeling. So designing combinational circuits and designing synchronous circuits like counter design, register design, flip-flops, all these things. So these are the softwares that we generally use for CPS. So in this, we are going to see these two and Sumo. So this we will be seeing it apart from Node.js. So Node.js is a kind of IoT come CPS softwares. Okay. So now, if you see CPS versus embedded system, we call embedded system plus physical environment equal to cyber physical system. So physical environments, it is sensors and actuators. Okay, and embedded systems, it is software with the hardware plus hardware, where the hardware is controlled by the software. So this is embedded system. So totally together we call it as cyber physical systems. Actually, morning I had a D1 slot, so I showed them some real sensors because I'm having it in my room in my office. So I showed them. So maybe next class I will show you what really how a sensor looks like, how an actuator looks like, and how a real sensor network works. I'll show you that. Maybe in next class I'll show you. Okay. So then some of these smart examples of CPS, electric grid, smart transportation, smart buildings, smart medical technologies, next generation air traffic management, advanced manufacturing. So most of these things are smart here. So electric grid means power supply. The distribution of energy comes from the grid. So if you take Chennai, between Chennai and Andhra Pradesh border, there is a grid. So the grid is part of Andhra Pradesh. So via that electricity comes to our Chennai, but it was not smart. So I have visited that some years back, but that was not smart that time. But I don't know about now. What is the status on that? Smart transportation is based on the GPS location of the bus. So whenever you go on a bus or a train, so it will always tell you the GPS location of the vehicles. As someone somewhere is waiting for a train or a bus, so they will get a SMS that this bus is approaching this. Even in our campus also, some students have done long back. Some students have done a project on CPS. So the day scholars waiting for the bus, they get an SMS or they get an SMS when the bus is approaching them. I mean, almost 1 kilometer away from that, they'll get an SMS that the bus is at this location, like that. Buildings. So buildings with smart energy, smart, arresters. I mean, surge arresters. So any electric circuit should not damage the building, or seismic vibrations, that earthquakes arresting. So all these things happens on life of the building. life of the structure, how they build the structure, how the resistance to dust, air, all these things. So those things in smart buildings. Then smart medical technologies, wearing a watch, and then through the watch you can control so many parameters, or you can measure your heartbeat. Even sometimes you can measure your ECG also with the help of a watch or a smart band. Then next generation air traffic management. So this is on air traffic means it is on flight control. So flight control, how in an airport they manage the traffic. So have you ever wondered that how the flight control is happening in Chennai airport or the major airports? So if you say Mumbai, that airport every day around 10,000 to 15,000 flights are landing and then taking off. So see that how what kind of control they might be having. So similarly in all the major airports, those things are. So how they go for air traffic management. Then advanced manufacturing. So this is on the industry 4.0. Again, a perfect example of CPS, cyber physical systems. Okay, so whenever you try out any work, see whether your problem solves the purpose of our society. Accordingly, you can do that. Okay. So now next thing is, this is where the difference of all the four. So bottommost is embedded system. Okay. So this is an embedded system. For example, airbag. Okay. So airbags, you know, there is when your car hit a particular obstacle at a very high speed, the airbag pops out, and there is a condition there. If you hit the car with 40 km/h, then your airbags may not come out. So there is a standard there. So you have to go and hit it at a speed of 60 km/h or something. So every car have that. Only after that the airbag will be thing. So even if you go by 40 km and if it doesn't pop out, you cannot file a case with the car company because they have their own norms. Okay. And people are telling that don't go for Maruti, don't go for Hyundai, you go for Tata and Mahindra. They are 4-star rating and 5-star rating in crash test, like that. If the people are telling, but please understand, the crash test, global crash test is conducted at a speed of 64 km/h. You can see that the 4-star rated cars or 5-star rated cars, they will be hitting with 64 km/h. So that means as long as you are going in 60 km/h and if you hit it, then how the car sustains, what kind of injuries the people inside the car has when they wear the seat belt or not. So accordingly, the condition changes. But please understand, if you go and hit at 100 km/h, all these results will become invalid. And even 80 km also, it's not. So the standard testing condition is 64 km/h. So whatever the 4-star rating, 5-star rating, they all work out for 64 km/h only. Okay. So that is one good example of airbag. That means once there is some component get hit, then another event triggered that triggers to open the airbag. So that is embedded systems. Above that we have networked embedded systems. So the internal core is embedded. Above that we have networked embedded system. That means the entire systems are getting connected. So one good example is autonomous aviation. So that means autonomous aviation means the flight control, everything becomes autonomous. So you can see that sometime 20-hour flight journey and 24 hours flight journey with non-stop flights. So usually the pilots, they won't be driving all the time. Sometimes they put it in autonomous mode. That means they drive themselves. Okay. So that kind of facilities are available in flight control systems nowadays. So they use autonomous aviation. So that is on networked embedded systems. Above that we have cyber physical system. So here only our topic lies, cyber physical system. So we have embedded plus networking plus the physical systems. So where we have cyber physical system. Now cyber physical system, above that we have this IoT. So that means cyber physical system plus data and services. We call it as IoT. So CPS plus data plus services equal to IoT. So embedded system plus networking will be network embedded system. Along with that physical system, from here to here, we have physical system. See cyber, and above that we have this Internet of Things. Okay. So you now understand by this circle, you might have understand that what is an embedded system, what is a networked embedded system, what is a CPS, and what is an IoT. Okay. So don't forget this as long as you understand the design. Okay. So next thing is components of CPS. So this is A generalized diagram may be not suitable for all the applications. In a generalized components, what are the different components available? So generally, this is a physical environment. Okay. So physical environment means the sound. So there are many things: sound, microphone, then seismic sensors, accelerometer, then magnetometer, then a mercury sensor, HG, then humidity sensor, then temperature, then pressure, then air monitor. So there are many things. So air quality checking, that is not air quality checking. So these are all the physical environment. So for physical environment to sense it, we need sensors. That's why we need sensors. So for each and everything, there is a sensor available. Okay. So physical environment, that means if you want to capture the physical environment is completely analog. So everything is analog. So sensing all these things happen through analog signal only. So in that case, we need sensors to capture those things. So again, sensors also analog devices, but there is a conversion there using ADC, analog to digital converter, ADC. So before it given to ADC, we have something called as S and H circuit. So this circuit is very common, sample and hold. Okay. So morning also I just showed them an example on sample and hold. Okay. So what I do is, can you tell me what is this? I have drawn something in the diagram. What is this? Can anyone tell me?
Pulse signal.
Still more better.
Sinusoidal signal.
Yeah, sinusoidal wave. So generally we call it as sin theta. Am I right? So sin 30 is somewhere here, sin 60, sin 90, sin 120, and sin 150, and sin 180. Then again 210, 240, 270, 300, 330, 360. Again it becomes 0 here. Okay. So likewise 0. So now what I do is, this is a analog signal. So this is a sine wave analog signal. Now when I convert into digital, so what I do is, I'll get 160, then 90, then 120, then this thing, then it goes like this, then so it will be coming like this. So totally what I did is 0, 30, 60, 90 like that. I want to 360. So totally including this 360, totally we have 13 samples. So only 13 samples. So 13 samples, I will get a sinusoidal wave like this. Not so accurate. But in case if I take 0, 1, 2, 3, 4 up to 360, then I will be getting 360 samples. So that means my sine wave will be, so like this, I have so many lines for 360. Okay, still more accurate. But if I take 0, 0 0.1, 0 0.2, 0 0.3 like that, then I will be getting 3600 sample. So likewise, the number of samples will be keep on added every time, and the accuracy will be maintained. So in that case, since there are 13 samples, when you convert the signal, when one sample comes, the next sample comes, the next sample comes. So this will be held for some time by the circuit. That's what sampling and holding it. That's what the circuit is called as sample and hold circuit. So then after this moves, then the next signal comes. Next signal comes. It is something like a temporary storage. Okay. So when the signal comes, it will be storing it for a duration of time, then it will go. So inside that there will be a capacitor to store it. So generally energy storage devices are mainly capacitors. So a signal comes, a sample comes, will be held for some seconds, then it goes, then next sample comes like that. So this is what we call it as analog to digital converter. So ADC and sample and hold circuit. So generally many ADC devices use the same way. They have a sample and hold circuit. And in the sample and hold circuit, there is a challenge that what kind of sampling here, 8-bit sampling or 9-bit sampling or 10-bit sampling like that. Okay. So for adding 1 bit extra, you need to spend huge money for that. Okay. For that 8-bit ADC will be cheaper. 9-bit ADC is costly. 10-bit ADC is still more costly. If you want 12-bit ADC, it will be very much costlier for increasing 1 bit. Okay. So morning also I was telling it about it. Maybe before I come to this, let's say 1 GB RAM. So please understand this: 1 GB RAM in your computer will be equal to 1024 into 1024 into 1024. Okay, so totally GB means bytes. Okay, so this is bytes. Let me not convert into bits, let it be bytes. So this will be equal to 2 power 10 into 2 power 10, sorry, into 2 power 10. So totally it will be equal to 2 power 30. So I need to have 30 bits. So 30 bits for 1 GB RAM. Okay. Now, how many bits needed for 2 GB RAM? Any guess?
60 bits.
No. Any other guess? I want to
31.
increase to 2 GB
2
RAM.
for 31. 2 for 31. 2 for 31.
Yes, good. So what I do is here in this I'll add maybe I'll take some other color here. 2 into 2 power. So what happens here? 2 power 1 into 2 power 30, which is equal to 2 power 31. So now I will be having 31 bits. So what here happens? If I add 1 bit extra, the storage gets doubled. So for 4 GB RAM, I will have 32 bits. For 8 GB RAM, 33 bits. For 16 GB RAM, 34 bits. So adding 1 bit extra will be doubling the size of the entity, whether it could be memory or it could be storage or whatever. Okay. So this is what happening in the ADC is the circuitry also. So 1 bit extra will lead to huge cost of the device. Okay. Then those data will be processed and it will be going to HCI, human computer interaction. Then we have a D2A converter and it gives to actuators for actuating. Again, it's a feedback system. Again, the actuator comes back to the physical environment. So this is the component of cyber physical system. Okay, just it's only a blind circuit here, a blind block diagram here. For each and every case, this might get varied, but what are the different components of a CPS? These all these things will be there. Maybe some extra things will be there. As and when it comes, we'll discuss on that. Okay. So traditional control systems. So generally traditional control system, this you might have studied in your control system subject. So there is a P, there's a controller, there's a planter. So we have a position, the reference signal comes, and there's an error between reference and the original signal. Then the position will be corrected, and this is how the way traditional control system works. Okay. So based on the reference and the P is the position. So based on this, there's a error rate. The controller adjusts itself. So this is how the way traditional control system works. Whereas cyber physical system, you can see here, the controller, instead of that, we have a cyber system here, but there's a controller in a digital control system. Here we have the physical devices here. So here there's a windmill and the position. So how the energy is being generated. So this is how the way the cyber physical system works. So completely smartness, whereas in traditional control system, there is no smartness, but here in cyber physical system, it is completely smart. Okay. So storing of energy. So windmills. So now this is the month of August. So generally, the month of August is very good for particularly in the deep south. So if you go to Kanyakumari and those areas where they have a huge number of windmills. Now this is a period in which the amount of electricity produced by windmills are very huge because there's a wind is very high, very good wind and very high wind these days for the next 2 months. So it is very ambient thing. So in that case, earlier time we were using no smartness, but now even windmills also storing this energy and give it for distribution. Okay. So that is what the digital or cyber physical systems. So traditional distributed computing. So 4:45, another 5 minutes. Okay. So traditional distributed computing. So you can see here services, airline, hotel reservation, office automation, social networking, distributed infrastructure is transferred to users. So you can see that there are multiple applications where we do day-to-day life. The application services are there. Computing and communication infrastructure is there. Okay. So underlying infrastructure. So this is your mobile app. Through your mobile app, you are doing the different services. You can say Swiggy, you can take Swiggy or Zomato for food. Then this will be for food. This will be for e-commerce industry, e-com, food. Then what else you purchase online? Food, e-commerce, anything in online other than e-commerce, food. Anything else you think of that you are purchasing online? Tickets, travel tickets. Likewise. Okay. So even this was the reservation here, office automation and social networking. So these are all some of the application services, traditional distributed computing. How distributed computing were working in a traditional way. Now sensor networks. Physical world instrumented with the sensors. Okay. Now this is what happens here. So the application services here, the computing infrastructure and the same services. But here in this case, what happened? The services, and here it is physical world dealing with the sensors. More data, real-time data. Sensors provide data directly to applications. So that means one good example I'll just tell you. You go to a supermarket. So with this I stop. Okay, with this slide, you go to a supermarket. Okay. So let's say there's a very big rack in the supermarket. Okay, so rack number 1, 2, 3, 4. So 1, 2, 3, 4. So the rack number 1, which is in the higher level. I mean, the height of the rack is very too high that it is in the top here. Okay, this is 4 here. So generally here they usually have chocolates, then snacks. Okay, and here they have biscuits. Okay. Now number 1 here is some stationery items, pen, pencil, paper, blah blah. This. And here some household. Okay. Now what do? Is they deploy sensors here. They deploy another sensor here. They deploy another sensor here. They deploy another sensor here. Okay. Now this is one of the best inventory system. Okay. So based on sensors, I'll tell you how this happens. Actually, there was a pilot project done some around 7 years ago, in 6 to 7 years ago. I don't remember the exact date, but more than 5 years. In Chennai, in one of a mall here in Chennai near Anna Nagar, there was a mall. In the mall, one company was doing a pilot project on this. What do? Is they deploy sensors in the entire mall. Okay. So when chocolates are being selling in great demand, so they will take all the 5 days: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay, so during weekends usually the shopping will be high, in high spirit, because people only go to the mall during the weekends. So in the time the chocolates are being sold in major number in Saturday, Sundays. So what do? Is they give good offers on chocolates, and the sensors is checking the capacity of the chocolates. Once the chocolate level is going down, so the sensors automatically connected to a application services here. The sensor connected, and which in turn procure more. So they will be procuring more chocolates because it's been sold more. So next week also it comes like that. So likewise, they take business decision based on the sensors. Okay. So 7 years ago it was a dream, but now it becomes a standard, because when you think of something, or when you tell something to your parents, daddy, there is a new phone have come in the market called as OnePlus Nord or something, it have come. So if you just tell your dad, so in the next 2-3 minutes, when you open any of the app like Facebook or Google or anything, the OnePlus Node will be just will be there. So in your search or somewhere in the search query, it will be there. So how it happens? Your mobile phone is recording your. I mean, it's always listening to your voice, whatever you are talking. So accordingly, it suggests you. It will be displaying the particular device name there. So that's how the way the sensors are listening. So there is a sensor there sitting on your mobile phone. It keeps on watching you. It's just recording your voice, and those voice signals, if they convert into business decisions. So this is how the way the sensors work. Okay, and they did one more thing also. So let's say you purchase a Reebok shoe. You purchase a Reebok shoe today. Okay, and after a month you are just visiting that same mall and the same store. You are crossing the same store. So let's say this is a pathway you are walking. So by the time you reach the shoe showroom, you are getting a message pop up on your phone. Not a WhatsApp message, it's a message on your mobile phone. You open it, they are telling that hey, welcome to Reebok. We are giving 40% discount today. So you are getting a message. So how come it is? So that means some kind of business decisions they may able to take with the help of the sensors. So they may be using some GPS location sensors. If you enable GPS on your mobile phone, so it may track you, or it can be telling you such kind of discounts and other things. So this is a typical sensor network strategy that have been that can be done in many of the places. Now it's already happening. Now in this time it is already happening. So anyway, I'll just stop it here.